We're going to take some notes today on data analysis, and so you will want to jot some of this stuff down. It's things, kind of skills that you'll need throughout the year. Like I said, if you're one of the 2 people that's still finishing this up, again, try to wrap that up as quickly as you can so that you can catch up with the rest of us with the notes. The homework for tonight, and it's not really for tonight because it's not due until tomorrow, but you can start on it at the end of the class period today and then work on it some tonight if you like. It's going to be 102.3 Graphing and Reasoning Problem Set, and that is due tomorrow. That is the last tab in that Google Sheet. Hopefully you turned in the tab, or really turned in the Google form that accompanied the tab for the Chex Lab. If you did not do that, again, the bottom of each one has a link that you can use in order to submit your work for that tab. So if you did not do that for the Chex Lab yesterday, then you need to get that done as soon as possible, because as of right now, that means that it is a 0 in there, or it's late if you don't do that. So please make sure you're using those links. All right, as I said, we have some notes today. So here's a question that I want you to ponder. If I asked you the following question: if I drive faster, how will the stopping distance of a car be affected? How might you test that? If I wanted to know if there was a relationship between the speed at which I'm driving and the distance it takes me to stop my car, what might I do to test it? Yes?
I might drive 2 different cars at different speeds.
Okay, so drive at 2 different speeds and then see how long it takes to stop. Sure.
Well, I was going to add on to that by making sure you stop at the exact same time in both cars to see the distance and time it takes to stop at both cars.
So keep some things consistent, that way we can compare them better. So make sure you're stopping at the same point in time. Sure. Okay, those are both really good suggestions. And both of those are taking into account some of these variables that you need whenever you are designing an experimental setup. Okay, all experimental setups consist of variables. Some of these are intentionally changed, like driving at 2 different speeds. Okay, while others are purposely kept constant, like trying to stop at the exact same point in time. Okay, so that your results can be interpreted with validity. So this should be a review as we go over these terms. Independent variables, this should not be the first time you were hearing that term, but again, you might want to jot it down. An independent variable is the one that is changed or manipulated in an experiment. In the previous example that we just looked at, the independent variable would be the vehicle's speed. It's the variable we determined before the lab even started and what we changed intentionally in order to figure out its effect on the other variable. In terms of a graph, because a lot of times when we gather this data, we're gathering this data in order to look at relationships, we're going to want to graph it. So whenever you graph data, your independent variable is always on your x-axis. Okay, so, but again, your independent variable in that example is your vehicle speed. Before I even started, I probably would have said, okay, I'm going to drive at 10 miles per hour, and then at 20 miles per hour, and then at 30, whatever. Oftentimes that independent variable is determined even before you start the experiment, what you're going to actually do so that you can then gather your data. Okay, so independent variable, you need to know that term. The next one we need to know is dependent variable, which is going to be what is determined by the independent variable. This is what you measure during your experiment. So in my example, whenever we were driving at different speeds, we would be then measuring that stopping distance. We're trying to see, does the speed affect it? So we have to measure it in order to determine that. Okay, so in that example, the dependent variable is stopping distance, and if we were to graph our data in order to try to look at the trend or the relationship that exists, if there is one, then the dependent variable would always be on your y-axis. Okay, so again, you will see, or will be graphing some things in here, quite a bit actually, as we collect data throughout the year, different labs, all of that. So you do need to know the rules for graphing as well. Yes?
Would the independent variable be on the x-axis?
Yes. All right, so independent variable, dependent variable, and then the last one, which was also mentioned a second ago, are control variables. These are factors in your experimental design that must be kept the same so that only one variable is being tested at a time. Okay, so trying to make sure you stop at that same point along the roadway, or using the same car that has the same mass, okay, or the same tires or the same surface. I wouldn't want to test one of them on gravel and the other on dirt and another on asphalt. That's going to give me different results. Same weather conditions. I don't want a wet road in one and the other's dry. So these are different things that you have to consider, because if you were to do this test and you were to use, let's say, 2 different cars with 2 different masses, well, now I don't know whether or not my stopping distance changed because of the mass, or whether my stopping distance changed because of the velocity, or whether it was a combination of both. So in order to give you valid results, you do need to keep some things constant. That way only one thing is being changed, and therefore only one thing can be accountable for any differences that you see. Okay, so the things that you keep the same are called control variables. Here's some just example data, but when you do the experiment, let's say you gather some data, it looks like this. Okay, now I can tell that as I drive faster, my stopping distance is increasing by looking at this, but I can't tell exactly what that relationship is. So a helpful next step would be to graph my data. And so let's go ahead and talk about some data representation and what makes a good graph. So here is an example of a graph of that data that we just looked at, which again gives me a better idea of what that trend is. I can tell now, or I can see it visually, what's happening. Okay, so a good graph is always going to have axes numbered by equal increments and labels with numbers. So you'll notice my graph, I have numbered on my x-axis by 10s, 10, 20, 30, 40, 50, 60. And on my y-axis, I numbered by 75. It doesn't have to be numbered by the same thing. It needs to be numbered appropriately for whatever you are graphing. But it does need to be equal increments. And you should space them out so that you use most of the graph paper, whatever you're graphing on. You don't want to make a tiny graph in the corner. You want to spread out, like skip lines, whatever you need to do, but spread out your data so that it's easier to see the trend. For graphs examining a causal relationship, which means examining whether something causes something else to happen, you're going to want to include a trend line that approximates the relationship between the variables if one exists. I included a trend line here. It would be a line of best fit. It does not necessarily connect your dots, although mine pretty much does because mine was pretty much linear. But sometimes you'll have dots that aren't quite in line with the others, and you can still add a best fit line. Sometimes your data, though, isn't linear, in which case you would want to add a curve, and we'll talk about that as well. Okay, so when you look at this data, now in order for me to kind of get an idea of how my speed affects my stopping distance, I would want to write a mathematical model, which means I would want to write an equation for this line. Since this one appears to be linear, I would do that in slope-intercept form, y equals mx plus b, which means I would need to find my slope. So I need to pick any 2 points from my graph. This one happens to go through the origin, so that's an easy point to choose. But if it doesn't go through the origin, you cannot use 0, 0. Okay, but I am. So here are 2 different points that I chose on my graph. Okay, they don't have to be your data points. They just need to be points that you can kind of tell. You'll notice I didn't pick any of the orange dots. Maybe I could have if they were exactly on my line. But I went ahead and found my slope, rise over run, change in y over change in x, 56 minus 0 over 20 minus 0 gives me a slope of about 2.8 feet per mile per hour. And I got those units from my axes. I did y over x, that's feet over miles per hour, which means for every mile per hour faster I go, it takes another 2.8 feet for me to stop, okay, according to this data. I don't know how accurate that is, but that's what our data shows. Okay, I could then write an equation. Again, slope-intercept form is y equals mx plus b, but in this class, we're not going to write y or x because we're not measuring y or x. We're measuring actual quantities. Okay, so my y variable isn't y, it's stopping distance. My x variable isn't x, it's speed. So this is my equation. My stopping distance is equal to 2.8 times whatever my speed is plus 0 because that's my y-intercept. And I can now use this equation to calculate what my stopping distance would be at any given speed, or at any given speed what my stopping distance would be, vice versa. Okay, so that allows us to make predictions, even predictions that lie outside of the data set that we collected, or within them if I can't tell exactly, where this point is. Again, this means that it takes 2.8 feet to stop per each mile per hour of speed according to this data. Again, I just made up the data, so it's probably not accurate, but that's okay, just for illustrative purposes. Our conclusion from this would be the faster the car travels, the farther the distance it takes the car to stop, which we probably already knew before graphing it, just from our own personal experiences on the road. Okay, why do you guys think my y-intercept is 0? Any thoughts? Yes?
Because if you're going 0 miles per hour, it takes 0 feet to stop.
Perfect. If you're going 0 miles per hour, it should take you 0 feet to stop. Okay, so yeah, you would expect it to go through 0. Hopefully it does. If it didn't, that would indicate you have some kind of error in your data. If a car traveling 50 miles per hour takes 120 feet to come to a stop, what would the stopping distance be for a car traveling 100 miles per hour? Okay, well again, this appears to be a linear relationship, so I don't even have to go back to my equation for this. All I have to do is say, hey, if I double the speed at which I'm traveling, I would expect that to double as well. Okay, and you could look at it in terms of proportional relationships. What type of relationship is this? Well, it's a linear one. This one is specifically is directly proportional because it goes through the point 0, 0, but it is a linear relationship between those different variables that we have here. Again, according to that graph. Okay, so in that example, we had linear data. Again, that was a directly proportional relationship. Not all relationships are linear. There are 5 basic relationships you need to know for this class. Definitely want to write these down. Okay, so here they are. Okay, this is the shape that the graphs will make. Will it be perfectly this shape? Probably not. But you'll see a general trend that is shaped like one of these. Okay, the first example right here is no relationship. If you have no relationship between your x and your y variables, your graph is going to show a horizontal line. This is kind of ridiculous data because this is how does the spiciness of the food I eat affect my height? And of course it wouldn't. That's the point. There is no relationship between these. No matter how spicy it gets, I stay the same height. And so if you were to write an equation for this line, it would be y equals whatever your y-intercept is, however tall you are, okay, would be that equation. So again, that's your first relationship. For my height, I would say that h, since again we're not going to use y, we're going to use our variable height, equals, and then whatever that intercept is. For me, that would be 173 centimeters because I'm 5'8".
What did you get the 4 sensors to connect to? Because it's blocking graphical analysis.
Okay, so the second relationship is a direct or linear one. That's the one we just talked about. You're going to get an equation here, a mathematical model in slope-intercept form. That's y equals mx plus b. For this example, I have a graph that shows somebody's pay per the time that they work. If you're an hourly employee, your data would look just like this. The more you work, the more you make. Okay, and so again, I wouldn't want to use y or x or m or b. I'm going to use my variables. So my pay equals whatever my rate of pay is. Let's say it's $13 an hour times time plus my intercept of 0, because again, if I work 0 hours, I theoretically make 0 money if I'm an hourly employee. I'm not, but you guys might have jobs after school, and this would be kind of, if you were to graph your data, what you would expect to see. Okay, this third one is an inverse relationship. Okay, this is a graph showing the time it takes to get somewhere based on how fast you drive. Obviously, if you drive faster, it takes less time. So you have an inverse relationship between these. This one I'm not going to write an equation for. I'm simply going to state what that relationship is. This symbol, in case you're not familiar with it from your math class, means is directly proportional to. So this is red. Y is directly proportional to 1 over x. Okay, that's not an equation. It just shows the relationship between the variables. Meaning, if I were to if I were to drive like twice as fast, I would get there in half the time. Okay, it just shows the relationship between the variables. And again, my variables aren't y and x, they are time and speed. So I could say that time is directly proportional to the inverse of my speed. I could write that as 1 over s, or you could write it as s to the negative 1. The next graph you see right here, this shape, if you see this, is a squared relationship. And this is a relationship you should be familiar with. This one is showing the relationship between the radius of a circle and its area. Okay, and I would expect everybody to know the equation for area of a circle, hopefully. Area of a circle is pi r squared, and so that means that we would get a squared graph, where my y variable is directly proportional to my x variable squared. But again, I don't have y and x, I have area is proportional to radius squared. And again, that matches the equation because the equation says area equals pi r squared. Okay, so this is just showing the relationship. It took pi out of it because we're just looking at how radius affects area and vice versa. The last one is showing a square root relationship. Again, if you see a graph like this that has a curve that kind of levels out as it goes up, that is indicative of a square root relationship. This one is, hey, as I go higher, like if I'm climbing a mountain, I can see farther and farther away, but it tapers off. There's only so far that I can see, and so you have a graph that is shaped like this. We would say that y is directly proportional to the square root of x. You could also take the variables and say that your sight line, that's my y variable, is directly proportional to the square root of my altitude. Okay, and that would be your fifth and final relationship. So those are the different relationships that you might see with our data as we go throughout the year. And you can recognize what they are by looking at the shape of a graph whenever you collect data and graph it in a lab. So again, have these in your notes. All right, so looking at equations, you should also be able to label the mathematical relationship. So this one says label each relationship and identify the effect on y when x is quadrupled. I'm going to give you guys some time to look at these, maybe even discuss with your neighbor. I would copy them down because this is often how these types of questions will appear on a test or a quiz. So I'm going to give you 41 seconds to discuss with your neighbor how you would answer this question. So turn and talk to them if you're not sure. Write out your answer. Be ready to be called on.
Yeah, because like multiplying one factor by 4.
All right, hopefully that was enough time for you to at least talk about a couple of them with your neighbor. All right, does anybody want to volunteer to answer number one? Go ahead.
On number one, if you multiply x by 4, it increases y's value. I don't know if it's like necessarily.
By what factor?
I believe a factor of 4.
You are correct. This is a linear relationship. That's the mathematical relationship part. And if you were to quadruple x, it would also quadruple y because y is directly proportional to x. So you'd have 4 times the y value. Perfect. Awesome. All right. Anybody want to answer number 2? Different person. If I don't have volunteers, I'll just pick a random name. Yes?
Oh, y would be 1/4.
Okay. Y would be 1/4. What type of relationship is this?
Inverse?
Inverse, where y is proportional to 1 over x. And yes, you can look at this proportionality statement and plug the 4 in there, and there's your answer, 1/4. Okay, you can do it with this one too. Your answer is 4. Okay, but you'd have 1/4 as much for whatever that y value is. Volunteers for number 3. Yes. Okay, what type of relationship is it first? Squared. Okay, which means y is proportional to x squared, and then you said how much? 16 times. Because if you were to quadruple this value, it is being squared. So it is not 4 times, it is 4 squared times, which of course is 16. Perfect. Anybody want to volunteer for the last one? This is the trickiest one, so yeah.
Would it decrease by 16?
It would decrease by a factor of 16 because this is actually both inverse and squared. So we call that an inverse squared relationship. It is possible to have 2 different things happening with those. okay, where y is proportional to 1 over x squared, which means it would be 1/16 as much. Again, if you can write this proportionality statement, you can put the 4 in there and you can see the fraction, 1 over 16, because it's 1 over 4 squared. Questions about any of those? Okay, again, it'd be a good thing for you to have added to your notes. All right, guys, so you can start on this Google Sheet assignment today for the rest of the class period. We get out of here in about 5 minutes, though, so you wouldn't make it very far, but you could. But 102.3 is not due tonight. It is due tomorrow night. We have gone over some of the stuff that is necessary to get you started, so you are welcome to get started right now or get started when you get home, but you do not have to do the whole thing tonight.